Swayam Prabha. Digital India. Educated India.
I have started delivering some lectures in module 6 of this course, which is about extraction of metals from sulfide ores. And we have already discussed copper extraction. Let me go back to the beginning once again and make some general comments. The reason I am going back is because sometimes you understand some general statements better if you know the specifics, and sometimes it is the other way around. For example, you understand the specific steps better if you know the principles, and once you know the principles, you know the specific steps better. So, actually in learning we have to keep on doing this, go back to principles and some general observations and go back to some specifics. Let me give you an illustration of that. What you must have noticed when we are discussing extraction of copper is that not only our aim was to get copper out of copper ores, but many other elements as such. Now, remember what I mentioned in the beginning, that sulfides are very good solvents, not only for each other, but also they dissolve other things like precious metals. Now, we have talked about processing of chalcopyrite. Which is sometimes written as Cu2s Fe2S3, or you can also write it as Cu Fe S2. We write either way. When we come to the extraction of zinc, which I will take little later, this is the ore of copper. For zinc, we have sphalerite. That is the main mineral, and lead mineral, main mineral is called galena. Now, it so happens that many deposits has more than two of these. You can have a sulfide deposit with bit of this and this, or all three of this. There are some which you call mixed sulfides, where all three are very much there together along with many other things. But generally we find that zinc sulfide and copper sulfide, sorry, this is PBS, zinc sulfide and lead sulfide often go together. Now, you know the sulfide deposits are found in Rajasthan. That is why we have the zinc plant in Udaipur. Now, it so happens that in the deposits where we have both ZNS and PBS, we can have concentrate rich in ZNS separated out by differential flotation. This can be separated out also by differential flotation, means a zinc sulfide concentrate and a lead sulfide concentrate. This goes to a zinc plant in Udaipur. It goes through and hydrometallurgical route. Zinc sulfide is first roasted, made into zinc oxide, then it is dissolved in acid, sulfuric acid, and from that acid solution, after proper purification, we electrolyze the solution to get zinc. This cannot be done for lead sulphide. What is done is now, this lead sulphide comes all the way to Bihar, to a place called Tundu. This lead sulphide will be roasted to PbO, and this will be reduced by coke in a blast furnace to produce lead. So, see the interesting thing, we have zinc sulphide, lead sulphide together in Rajasthan. Zinc sulphide will go for treatment nearby, whereas lead sulphide has come all the way to Bihar, because we need coke. So, the question is either you take coke to that place or you bring this to this place. Lead is also produced in Vizag, again the concentrate comes from that place to Vizag, unless it is imported. Copper pyrites, which also is kind of mixture of iron sulphide and copper sulphide, can be found as a rich concentrate in eastern India. That is why we have a copper smelting plant in Ghatshila. But there are many deposits in India where all three are together. I will come to that towards the end, and till today we do not have a very successful commercial process for exploitation of these, for various reasons, maybe their location, maybe the extent to which they are there, or the complications that one has to go through to handle three elements from them. But this is very successful. When you have zinc sulphide and lead sulphide together, they can be separated out by flotation. One goes in one way, the other goes another way. Now, there is also a very important process called imperial smelting process, which I will discuss, where in Rajasthan itself there is now blast furnaces which are called imperial smelting process, where a concentrate which has both of these can be treated. Lead will come out by carbothermic reduction. During that reduction, zinc will come out as a vapor from the top, and there is a way of recovering zinc from that vapor. We will discuss that. That is a very modern process for production of zinc and lead from the same unit. In theory, if there is any copper in that concentrate, that can also be recovered as a separate phase in imperial smelting process, but normally it is not a very desirable thing. What I am trying to say is that these sulphides are often mixed together, and by differential flotation we can have concentrates that are rich in 1 or 2. Generally, we will like to have a concentrate which is only rich in one metal, main metal, so that there is a well defined process. But imperial smelting process can handle a concentrate containing both zinc sulphide and lead sulphide. Now, you will appreciate now what is happening in sulphide metallurgy. In sulphide metallurgy, the main elements involved are copper, lead and zinc, and we recover all 20 elements during their processing. Copper, lead, zinc of course, depending on the main element, then sulphur, silver, gold, platinum, palladium, arsenic, antimony, bismuth, selenium, tellurium, nickel, cobalt, indium, tin, rhenium, mercury, all these are recoverable and they are recovered. You recall the flow sheets I have shown for copper refining, many of these are coming out of that. Now, the elements, they are also there, but they will be discarded, because they would not have commercial value even if discarded are these. So, we say in addition to these 20 recoverable elements, there are at least 9 other elements which must be separated, usually in the form of a discard slag or gas. at one stage or other of the processing step. And very interestingly, the elements that we are utilizing mainly in the processing of copper, lead and zinc are carbon, oxygen and hydrogen in the form of water. Now, we will go back to copper again and see the relevance of the statement we have made. Now, we have seen that so far as copper metallurgy is concerned, we start with an ore which is only about 1 to 2% copper. On it has to be first ground to fine size, then flotation upgrades it to 15 to 35% copper. Then the conventional route has 3 main steps. One is roasting, then reverberatory smelting and converting to finally get an intermediate product called blister copper, which on refining will produce cathode copper, very pure, and a whole lot of byproducts in the slime recovered. Now, there is another minor step sometimes called calcination, which is not a very important step, and we can ignore that for now. The first step of roasting, which can be in a hearth roaster or in a fluid based roaster, you should understand by now. There the main point is to heat the concentrates without fusion in the solid state. The main idea is to oxidize the concentrate, so that most of the iron sulphide is taken to the FeO stage, preferably not beyond, because if it goes beyond FeO, then subsequently we will find it difficult to remove them through slagging. So, to ensure that it does not get over oxidized, we have to leave a lot of iron sulphide unoxidized. It is okay. Now, this is a oxidizing step. You need oxygen to oxidize the concentrate. Next main phase is reverberatory or electric furnace smelting, where a liquid phases are formed. We add fluxes, so that we have a slag. In that slag, we will take the FeO that was created here, and some more of the iron sulphide that was left behind would also be oxidized, taken to a FeO step, and we will try to remove as much of iron as possible in the slag here. Essentially, we will be left with a matte, which is a mixture of copper sulphides and iron sulphides, with very little of oxygen left, very little of FeO left. Now, during the converting, whatever that FeO iron sulphide is remaining in the matte will be oxidized, taken into a slag phase. The slag phase will go back here, because there could be some copper coming out. So, we have to recover that. So, finally, a stage comes where all iron sulphide has been oxidized, and that process of oxidation provides heat during converting, which becomes an autogeneous process. We are left with what is called white metal, that is all Cu2s. Now, this Cu2s starts getting oxidized, starts forming Cu2O, and when we have twice as much Cu2O as Cu2s, they react mutually, starts forming copper. Copper will settle to the bottom. Because it is settling to the bottom, we cannot have bottom blown converter. So, the converter is side blown. And finally, we have to find a time when all that copper sulphide has been converted to copper, and mind you, there is no reducing agent involved. You are simply oxidizing copper sulphide to form Cu2O, then Cu2O and Cu2s is reacting to give copper, it will form blister copper. Now, obviously, we have an oxidizing atmosphere here. In the reverberatory furnace, we do not need such a strong oxidizing atmosphere, because mainly we are removing the FeO in the slag stage, but we want a stronger oxidizing atmosphere during converting. So, there are 3 stages with different PO2 requirements. Now, the advancements in copper metallurgy aim at combining these steps. Why do we want to combine? To understand that, look at this slide. So, this is a conventional route. We have the concentrate goes to roasters. Now, after you have roasted the material, has to be taken out, transported to a reverberatory furnace, where you are making a mat. After you have made the mat has to be transported through ladles into a converter to form blister copper. So, there are transportation operations involved between roasting to reverberatory furnace to ladle. So, you have 3 steps, and during this intermediate gaps you lose a lot of heat. You just take out hot material from here, you charge here, you are losing heat there, you take out hot material from here in ladles. Not only you are adding operational steps, you are also incurring lot of heat losses. So, the attempts have been made to combine these steps. The first step in that direction was the flash smelting, that the after you have got the concentrate, they are dried, and then there is no separate roasting and smelting. It is all done together in a flash smelter, where in suspension all the reactions take place. In one stage you produce matte, and that goes for converting. So, you are producing in one step matte. Now, the third generation wanted even to combine these two into one. So, that we start from concentrate and in one reactor go straight to blister copper. This is called the continuous smelting route, and many developments have taken place in that direction. The idea will be to take the concentrate, and in one reactor it will be continuously smelted, means it will undergo roasting, smelting, converting, and straight away it will produce blister copper. Now, there is we cannot think of a process which will combine refining also in all this and produce refined copper. That is not possible, because these are pyrometallurgical processes, whereas refining combines pyrometallurgy and finally electrometallurgy. But 1, 2, 3 steps can be made into 2 steps in flash smelters, and all 3 can be combined into one reactor in continuous smelting operations. What will be the advantage? That you will get rid of the going from one stage to the other, transporting material from one to the other, having heat losses. And once you have one reactor where everything takes place, things can be faster, speedier, heat losses would be low, but things will be more difficult. Why they will be more difficult? Because here is a reactor where the condition can be uniform, same PO2 will prevail in the roaster, is roasting. One PO2 will prevail in the reverberatory furnace, and during converting you are injecting oxygen, there is certain oxidizing environment in the converter. If you want to convert these 3 into a single reactor, then a reactor must be so designed that its partial pressure of oxygen varies from one region to another. So, it is not a reactor where the gaseous atmosphere is uniform. It is not possible to then go from concentrate to matte to blister copper. So, the reactors have to be designed with notionally separate regions. They are connected all right, but they are separate regions where roasting, smelting, sometimes roasting, smelting can be combined as in the flash smelting, but definitely smelting and converting are two different operations altogether. Now, a simple way of doing this was done by the Japanese. The Japanese proposed a smelting process called Mitsubishi continuous smelting process, which actually was a continuous process, but not necessarily one reactor. No, they had 3 reactors, but the interesting concept was that there is a smelting furnace where flux, air, oxygen as you say injected, combine roasting and smelting in one step. That can be combined, roasting and smelting in one step. Then the slag and matte they flow out, because the next reactor is put at a lower level. So, these automatically flow out, and this intermediate chamber is called an electric slag cleaning furnace. Means you have got the slag and the matte, but the slag can be treated to get the right temperature under right PO2 to recover all the, if there is any CO losses, and there is a baffle here you see which dips into the liquid, which means only the matte can go from the bottom to the other end, but the slag gets stuck here. Slag floats on top, the slag cannot go that way. There is a porthole through which slag would come out and for dumping. So, this intermediate step is to ensure that copper losses in the slag are minimized, and the slag is not allowed to flow to the next chamber because of a baffle is taken out. Only the matte can go under the baffle and flow into the next reactor, which is again at a lower level. So, these 3 go from one level to a lower level to the lowest level. So, the matte will flow from here into this slag. If there are any copper, that copper will be recovered, that matte will go here, and then this is a converter where air, oxygen, calcium carbonate is are there, and you get blister copper, and the converter slag will be granulated and it will go back here, just in case there are some copper losses. Now, this is a kind of continuous process in the sense that continuously concentrate is being fed, continuously blister copper is coming out, but the whole thing is not a single reactor. But this is easier to operate, because you can maintain a very high oxygen partial pressure here, the oxygen partial pressure here required is low, and here it is a conditioning compartment where you have the PO2 as you need in order to recover copper. So, this is the Japanese process, but this is not the ideal solution. One of the first answer to this question of combining all the steps was provided by a man called Werner, and the process is named after him. It is called Werkra process. This is derived by combining the first 3 alphabets of the inventor's name Werner with CRA, which is Conzino Rio Tinto of Australia Limited. It is an Australian company where Werner was working. So, he conceived the idea. There are many others who were conceiving the idea, but he finally developed a process which was workable. The process seeks to maximize the conservation of energy obtained from smelting and converting by integrating to a high degree a continuous operations. Now, I have mentioned earlier that all the reactions that are happening during sulphide processing are oxidizing. Whenever sulphides get oxidized, they produce heat. But if you have different stages, then much of the heat generated in one step will not go into the next step, because in between you lose that heat, especially when you are transporting material, or if you have too many units from the surfaces of which heat gets lost. If you put them all in one reactor, then heat losses will be minimized and you will make better use of the heat being generated in the smelting and converting operations. Now, this is the scheme. This is a Werner Warcraft furnace, where POT will not be uniform all through. We will tell you how. And schematically, it has to have air injection. Whatever heat will come out will go through heat exchangers for recovery of heat. The gases, that is SO2, that will come out will go to an acid plant to make sulfuric acid. This is flux SiO2 concentrates, these are going into here. Oil or coal, this is for supplying heat. Now, one of the very interesting concepts to be used in a continuous furnace is that the partial pressure of oxygen cannot be uniform all through. This is another interesting concept which needs some engineering, that is that matte and slag phase must flow in opposite directions. You cannot have matte and slag flowing together and coming out at the same end. In all these reactors, you will find matte is coming out on one side, slag is flowing out from the other side. Why this is so? The two basic principles of a continuous operation will be that one, in the reactor, partial pressure of oxygen will not be uniform all throughout. And the other is there must be counter current flow of matte and slag. Now, what is the advantage of counter current flow? For that, consider the drying of a slurry by air, hot air. Now, in concurrent flow means where the slurry and the hot air are going in the same direction. Schematically, it is like this: hot air and wet slurry. If you plot the moisture content as a function of distance, the air is initially very dry. So, it is going to pick up moisture as it moves along, whereas the moisture content is very high and it will gradually, the slurry will gradually lose moisture content. Now, initially the driving force for drying is very high, because there is a big difference between the moisture level in the slurry and the moisture level in air. But after some time, the driving force comes down, and therefore, the process is not very effective any longer. Whereas, in the counter current flow, the wet slurry is moving in one direction, the hot air is moving in another direction, and there the picture would be something like this: moisture content, is the distance, hot air is going to pick up moisture, whereas slurry is going to lose moisture with distance. Now, here the driving force will remain almost uniform for a long distance. So, if you allow it to flow, counter current flow is very effective in bringing one phase from one layer to the other layer. This is the basic principle also in the case of counter current flow of slag and matte, because we want matte and slag to react and ensure that any copper in the slag phase goes into the matte phase. How will it go? One of the ways, as I have mentioned, is FeS will react with any Cu2O in slag, form FeO in slag, and copper will be recovered and it will go to the matte phase. So, we need a counter current flow of metal and slag, and for that some simple engineering techniques are employed. I will now come to some configurations that are applied in worker furnace design. There are many kinds of designs available, and let me also mention Werner was one of the first to suggest a continuous operation, and he called that plant Werkra, but subsequently many other continuously operating plant designs have been proposed and some are working successfully. Of course, Australia is a leader, and there is a process called Aus smelting for continuous operation of copper, but there are also many others. All of them make use of two basic principles. PO2 will be different in different regions in the same reactor, and slag and matte must flow opposite each other in contact with each other. So, that finally, when the slag is discarded, it has the minimum amount of copper in it, and the matte that is recovered has the maximum copper recovery. Let us go look at one or two designs. Here are two designs of worker furnace. One is a U-shaped design, the other is a straight design. Now, in this design basically there is a smelting bowl. This smelting bowl is where we are combining roasting and smelting of the concentrate, and the matte that is being produced is moving in this direction. How it is made to move, I will come to that, and the slag is made to move to that direction. Now, here some more concentrate is poured in to ensure complete copper removal, because if the slag is carrying some copper, reaction with concentrate will recover that copper to produce matte, matte will again come back here. Finally, there is a slag cleaning zone to ensure that it is cleaned of any residual copper, and slag goes to a well, matte will go to this area where there is a converting, very high PO2 here, there is less PO2, something intermediate here, and this is a straight design. You have converting zone in one side, smelting zone here, slag cleaning zone there. Slag is moving that way and copper is moving that way. This is the elevation, this is the plan. In the elevation you see concentrate in, gases out, smelting zone, slag goes this way, matte goes that way, this is copper comes here, slag comes out here. We are getting blister copper, mind you. Now, this is the plan view. There are this is the way the thing is made to circulate continuously. Air oxygen will be blown in the converting zone, these are the fluxes going in. This is the slag cleaning zone, where again we will put some concentrate, if necessary some reductant. If there is some CO2, you must get that copper out by reduction of the CO2. So, here the our PO2 level has to be very low, here it is very high, here it is the highest, here it is intermediate. Now, how do we ensure that copper and slag move in other direction? The simple technique for that is the following. We know that slag is lighter and matte is heavier. So, in a reactor, if we put a baffle like this, then slag cannot flow that way, it has to flow this way and matte will go that way. So, matte will be go this way and we do not have this, slag will flow that way. So, whenever we have this slag and matte, slag layer is building up, we do not allow it to go to the side where matte is going, by simply have a baffle which dips into the matte. The matte will always can run through, but the slag cannot penetrate this. The slag is made to flow that way. We can even make it easier by providing a gradient here. So, the matte flows more easily, slag has to flow to the other side. This is a very simple engineering thing which you will find in one or two designs. Now, let me read out one or two things here. The concentrate particles possess a large surface area which helps in accelerating reactions with a gas, liquid or another solid. The worker process also seeks to reduce the capital and operating cost by eliminating handling of solids and liquids in batches. A single furnace combines the following operations. They occur in separate but interconnected zones in the same reactor: continuous smelting, continuous converting, continuous slag cleaning by conditioning and settling. I have compared the traditional approach and the worker approach. Now, there are several variations of worker. The sole aim in each is achievement of compartmentalization of 3 unit operations. It could be in a horizontal plane, it has to be done, and we have shown you two, one U shaped and the other is a linear version. Again, the main characteristics are that the process directly produces a metal rather than a matte from the concentrate. The heat of the exothermic oxidation reaction is utilized in the reaction itself. Now, many such continuous smelters have been proposed, and in my book I have given a comparison of the smelting rates in different copper smelting reactors. It is difficult to make a direct comparison, because reactor shapes, sizes, etc., are different, but one way would be to compare specific melting rate, which is tons per day per meter cube. There are some reverberatory furnaces where the green charge is put, means without drying the concentrate is introduced, and in some it is first calcined, means dried and then introduced. Obviously, the specific melting rate will be more if you have calcined charge furnace volume. They are more or less the same. Actually, in green charge specific melting rate is a bit higher, because I think somewhere there is some heat generated. Now, in the flash smelter, like one Outokumpu flash smelter, one can have preheated air or oxygen enrichment in the reactor environment. Obviously, if there is oxygen environment, specific reaction rate will be, smelting rate will be much more. See, it is about 4 times that of the conventional reverberatory furnace. In Mitsubishi continuous smelting, it will be about 3.41, but in other kinds of continuous smelters, there is one called Noranda, which I will show you, it can be much higher. And now there are also other reactors where these operations are much faster. Let us consider one. This is the vertical sectional diagram from one kind of a Workra reactor, which again I will show you that engineering principle, that there is a baffle here which will not allow the slag to come that way, but matte converted copper, blister copper can come under the baffle and come out this way, whereas the slag can flow to that side and the slag can be taken out. There was a process called Noranda process, which was developed in Canada. Again, similar in concept, you will find that matte is coming this way, slag is coming from that side. Again, there is this baffle going into the matte slag phase, so that the slag cannot go to that side. Here also there is a two-air zone. This is where the converting operation takes place. This is where we will have the smelting operation. It's clearer here. This is the reactor. Copper or matte is coming from one side, slag is being taken out here, and some of the other details, not necessary. Okay. Now, there are so many processes for copper smelting, and next I will also come to the hydrometallurgy of copper. And people would like to know which process will require more energy. How do we analyze the energy requirements? For that, Kellogg gave a very interesting concept. He proposed that we use a thing called process fuel equivalent to compare energy requirements. Initially, he did it for only the copper metallurgy, but now it has become of general use in many extraction processes. So, the concept introduced by Kellogg says this, that we should consider a term process fuel equivalent, which is a summation of 4 terms F, E, S, B. F is quantity of fuel directly consumed by the process. Are you using coal? Are you using fuel oil? And what is the heat value of the fuel you are using? That is what you are consuming. Are you consuming any electricity? If you are consuming any electricity, then E, what is the fuel equivalent of the electricity? And for that there is a well known conversion, that is 2650 kilocalories per kilowatt hour, which is the normal energy need to generate power from fossil fuels. So, the energy input into the system in terms of solid or liquid fuel or electricity, you first calculate. Then we calculate S. S is the fuel equivalent of major supplies used in smelting as reagents, oxygen and fluxes. This is something that one usually forgets, that in a process you have brought in some raw materials, but the raw materials have not come out of nothing, they have come out of something and they have needed energy for their processing. So, you have to find out how much of energy was required to produce the raw materials that you are using. For example, you are starting with the copper ore. you are grinding the copper ore. So, you need to know how much of energy you have required in grinding. You find the fuel equivalent. Then you are doing flotation. For flotation, you are blowing bubbles, you are using pumping, there are the liquids have to go from here to here, the slurry has to move from here to there. How much of energy is required in that? Remember, in the very first lecture, I had said that initially when we were undergraduate students, we were told that if you reduce an oxide by aluminum, the aluminothermic reduction is highly exothermic. You do not have to supply any heat, you simply ignite and everything would automatically, the oxide will get reduced to metal. What we were not told at that time is that it is not really a process which is very friendly from the energy point of view. In that step it is fine, but then you have needed energy to produce that aluminum to start with. You cannot ignore that. That is why we cannot always say that a raw material is a zero energy source. Consider steel making. In steel making, you can produce from iron ore to steel, you need energy. Suppose you find scrap steel lying around, which is nobody is using, you take the scrap, you produce steel, you will need less energy, because the scrap is already impure metal, but then it is not being used, it is a zero energy source. But suppose you are not getting scrap and as a scrap substitute you produce sponge iron. In sponge iron plants, if you produce sponge iron, which can go in for electric furnace smelting, but sponge iron is not a zero energy source. It has needed a lot of energy for processing of iron ore reduced by coal to produce sponge iron. So, if you want to analyze the energy production for steel making electric furnace steel using sponge iron, you have to take into account the heat that has gone into making of the sponge iron to start with. Similarly, in copper smelting, we have to find out the energy required in the production of raw materials that are using. It could be copper concentrate, the fluxes. If you are using oxygen, then you have required energy to produce that oxygen. When you are injecting that oxygen, you need power to inject that oxygen. That will come later. That comes under the fuel requirement in the process, but the oxygen as a raw material also has a energy equivalent. Now, so these are the energy inputs. Now, B is the fuel equivalent of byproducts and useful surplus heat. If there is an exothermic heat, that will come there. If there are hot gases coming out from which you can recover heat, if there are hot materials coming out, there is a fuel equivalent that has to be taken out. That is a thing of an advantage, these are disadvantage. So, process fuel equivalent has to PFE has to take into account the fuel inputs directly, indirectly through raw materials, and the energy that you are getting from the heat of reaction and from the heat value of the hot products. Now, a very interesting thing has been found that you are using in converting air or oxygen, and in the process in many places, whether during roasting or smelting, you are maintaining an oxidizing atmosphere. People have made a general analysis of what role does oxygen play in terms of PFE. It has been found that oxygen enrichment effect on energy used in copper smelting, the more oxygen is used per ton of anode copper final step, the less is the PFE value. What does it mean? Means as far as possible one should use oxygen enriched air or oxygen, then the total energy requirement becomes less. From common sense we can tell why, because when you use air you are heating up a lot of nitrogen which has no role in the process. It takes a lot of heat, then goes out and hot nitrogen with whatever air is escaping. If you eliminate that nitrogen part, enrich air with oxygen, your heat efficiency becomes better. Now, here the comparison is made between wet concentrate charge reverberatory furnace, calcined charge reverberatory furnace, electric furnace smelting, then Mitsubishi continuous smelter, Noranda with no oxygen enrichment. So, we have put all kinds of things, and generally it is found that if you have oxygen enrichment, the process will be better from energy point of view. Now, this is all about the pyrometallurgy of copper. Now, 85% of world's copper production is by pyrometallurgy, and of that I think the most is by the conventional route. Of course, using flash smelters, I mean it is now become the middle stage is more common. Nobody now uses a reverberatory furnace and then means roaster, reverberatory furnace and converters. The first two have been combined in many places, including the copper plant in Ghatshila. But continuous copper production is still not that common, because it needs more control obviously. You need sensors, you need computerization, because you need that an input material must always remain of the same composition, because if there is any variation there, then the entire chain of operations will suffer. But 85% is still from one or other kind of pyrometallurgy. But then hydrometallurgy can also be employed in extraction of copper, and for that the common process is ferric chloride leaching of copper pyrites to take copper into solution, and then that will become our starting point. I will come to that in the next lecture, but in a passing I will just mention one thing, that in the copper mines it was found sometimes that when you have taken out the pyrites, mine is abundant. After many months or years they find that when rainwater is accumulated, it has turned blue. Apparently, it has leached the residual copper sulphate that was in the abundant mines. And then people discovered there are some natural bacterial reactions which cause this. This is called bacterial leaching of copper ores, and found accidentally. Now, it is also being employed in many places, but it is a slow process, particularly suited for low grade copper ores, where there are certain kind of bacteria, if they are introduced, they are called ferrobacillus ferruxidans. There are other bacteria whose job is to convert the minerals into soluble sulfates. I will not discuss that, but in my book there is a reference to bacterial leaching of copper ores or bioleaching of copper ores. They are also applicable in case of uranium ores, but they are of course not commercially as important as other processes, as the ferric chloride leaching process that I will discuss in the next lecture. Thank you.